Now that we understand a little bit about what chemistry is about, and we've learned to at least work somewhat with the system of naming and symbols that we use for chemistry, it's time to start going to the next step, which is understanding chemical reactions and trying to predict the products of reactions. It makes sense to start with a type of reaction in which you're putting things together to make a new substance. So in a synthesis reaction, you would be combining two things, forming bonds between them to make one more complex thing. We can also do the opposite. We can take a complex part apart, break the bonds, and create smaller components of that. That would be a decomposition reaction. We can also do something called a single replacement reaction, where we take an element and we add it to a compound. Depending on the identity of element A, it could replace B. So if A were a metal, for instance, it could replace the cation part of that compound B and form AC, in which case B would be by itself. If A were a nonmetal, then it would replace C, the anion part, and you would end up with Ba plus C. So two different options for a single replacement reaction. Next, we have a double replacement reaction. So in a double replacement reaction, you would have perhaps two ionic substances, AB plus CD. And in this case, we're going to have both ions switch places. So A would end up with D, and C would end up with B. So they would have a double replacement reaction. Notice that we maintain the first part as being listed first. Those are usually the cations, and then the anions, the B and the D, would be listed second. All right, so that would be a double replacement reaction. Next, we have a combustion reaction. While there are different types of combustion reactions, the majority of the ones that are kind of important to us on a day-to-day basis are the combustion of hydrocarbons. So for instance, if I looked at one of the components of gasoline, carbon and hydrogen, and this would be in a liquid state. If we combine that with oxygen, we would form carbon dioxide and water. And of course, we would have to balance that equation. But the idea is that you have a hydrocarbon, a compound that contains both carbon and hydrogen reacting with oxygen to form carbon dioxide and water. The hydrocarbon could also contain oxygen. And again, you would follow that same pattern of the hydrocarbon plus oxygen forming carbon dioxide and water, and then we would just need to balance that. So these are the 5 main types of classifications of reactions that we will use this year in the honors chemistry. An additional classification that we'll use to describe reactions can be examined if we look a little closer at this reaction here. So this is one that we did in the chemical and physical changes lab. Magnesium with hydrochloric acid formed magnesium chloride and hydrogen. And so you can look at this and probably identify the type of reaction this represents, which would be a single replacement reaction. The magnesium replacing the hydrogen, so the hydrogen off on itself. But it would be helpful for us to look at this in a more detailed way. So for instance, the magnesium right, which is a solid, we would leave as it is. But if we were looking at this on the particle level, I really wouldn't see hydrogen and chlorines together floating around in solution. What I would see are hydrogen ions floating around and chloride ions floating around. Likewise, on the product side, I wouldn't see magnesium and chlorides bonded together in the solution, in the aqueous solution. I would see magnesium ions, and I would see chloride ions. And then the hydrogen, again, as a diatomic, will be represented as such. Now, when you write it this way, you don't necessarily recognize that it's a single replacement reaction. It almost doesn't look like that. But what you do notice here is that the chloride ions really don't change, right? So those are our spectator ions. So I'm going to rewrite the equation without those. So we've got our magnesium, and we've got our 2 hydrogen ions, which are then going to produce a magnesium ion and a hydrogen molecule. Now, what becomes obvious here is that our magnesium, which started out neutral, now has a 2+ charge. So our magnesium must have lost electrons, right? And specifically, it must have lost 2 electrons. If we look at our hydrogen, hydrogen was, the 2 hydrogen species had a positive charge, so they had lost, they're deficient by 1 electron. Now the hydrogen is neutral, so the hydrogen must have gained electrons. Each hydrogen gaining 1 electron. So that loss of electrons by the magnesium is equal to the gain of electrons by the hydrogen. This shouldn't be too surprising to us. This loss and gain of electrons is another type of reaction called an oxidation reduction reaction. So you can see in this example, we have a single replacement reaction, but we can also describe it as an oxidation reduction reaction. A nice kind of mnemonic for remembering this is Leo, the lion, goes grr. Leo, the lion, goes grr. So the thing that loses electrons is oxidized, and the part that gains electrons is reduced. Right? So if we look at equations from the perspective of the ions that are dissolved in the water, it might be easier for us to identify what things are gaining electrons and what things are losing electrons, if at all, if that's even happening at all. But that would enable us to then classify it as an oxidation reduction reaction.